Welcome to the second lecture on Butler-Volmer equation. In this lecture, we will take a different perspective from that of the previous lecture. I want to emphasize that Butler-Volmer equation was developed in early 1900s. Okay, so this was the time when many of the analytical tools which we have, experimental tools which we have right now, was not at all available in those times. So the great scientists imagined a lot of things to come up with a theory of a quantitative theory of an electrode-electrolyte interface wherein an electrochemical reaction is taking place. In this approach, we will emphasize on the potential energy surface. We'll clarify this term. This is addressed in much greater detail in the last decade or so because of availability of quantum chemical density functional theory calculation. Okay, that has enabled exploration of potential energy surface. But at the time when Butler-Volmer originally framed these equations, they had to really be very creative to come up with what might be the relevant potential energy surface because much of the information that we can now access was just not accessible in those times. Again, to reemphasize, what we are looking at is the current electrode potential response. Okay, so as we change the electrochemical potential of the electrode potential, we are changing the ore voltage relevant to certain half-cell reactions. Here, there are two reactions mentioned. One is the oxygen evolution reaction and hydrogen evolution reaction. This has a particular thermodynamics calibrated by this equilibrium potential. This has a particular thermodynamics calibrated by a different equilibrium potential. Corresponding to the different O potentials for these two reactions, we can plot the rates. We want a mathematical description for the current variation as a function of the manipulated variable, which is the O potential. In effect, we are manipulating the electrode potentials. That's the objective. We took an approach which is based on chemical kinetics. Okay, so we appeal to many notions that you are probably aware of from a previous class in chemical kinetics to analyze electrochemical kinetics. That emphasized on measurements. Certain critical properties were obtained from experimental measurements. That has certain advantages, but it also has certain disadvantages. It is in a way less insightful from a molecular perspective. So whenever you want insight, the insight is always debatable. Okay, so that is the disadvantage. But despite the limitation, there is a certain power in the approach we are going to utilize in this lecture, which is based on potential energy surface relevant to an electrochemical system. Okay, so let's get moving. So as an example, we are going to utilize an electrochemical system on a single electrode-electrolyte interface. The electrode of relevance here is a platinum. We are choosing that because it is inert. Okay, so it plays just a single role of it being an electron reservoir. Okay, it can take up electrons and give off electrons. That is the central role platinum is going to play. We call it inert because you don't see any redox species relevant to platinum. Okay, it acts as an electron reservoir or electron bath, and you can vary the potential of the inert platinum electron. And the relevant redox reaction, electrochemical reaction, are given here. There is an equilibrium potential for this redox reaction. And when you go in an anodic direction, that when we increase the potential, the more oxidized species will be formed. Okay, so we have discussed these things in a previous lecture. When we addressed the thermodynamics of electrochemical system, we discussed what is called the dominance diagram. There we address this issue. When we go in the anodic reaction, you are favoring the formation of the more oxidized species. When we go below this equilibrium potential, thermodynamically, we are favoring the less oxidized species. So there are these two reactions, oxidation and reduction. Oxidation here and reduction here. That becomes thermodynamically favorable depending on your electrode potential, whether your electrode potential is above you or below you. Also, when we are increasing the electrode potential, that is when you are making it more and more positive, more and more anodic, we can imagine the electron density within the electrode to decrease. Okay, the opposite will happen when we are decreasing the electrode potential. When we are decreasing the electrode potential, that is when we are making it more negative or more cathodic, we are increasing the electronic energy levels in this direction. Okay, so many of these notions are intuitive from electrostatics. Okay, so you appeal to your intuition from electrostatics to get a better feel for how the electronic energy levels vary as you vary the electrode potentials. The dominant manipulated variable is the electrode potential, and that manipulated variable is going to control the electron transfer. In general, we can take a redox couple containing an oxidized species and a reduced species. Electron addition to the oxidized species will give rise to the reduced species. Moving on, we are introducing what appears to be an information-rich diagram. This is called the potential energy surface that is relevant to this electrochemical system indicated here. Oxidized species combining with an electron, giving rise to a redox species. We will introduce the x coordinate, x-axis. This again is borrowed from chemical kinetics. We are going to call this coordinate along the x-axis as a reaction coordinate. Okay, it's a measure of reaction progress. Okay, so as we move along this direction, it's an abstract coordinate. Okay, it is not a spatial coordinate, it's an abstract coordinate indicative of the progress of the reaction. Okay, so as we move in this reaction coordinate, we are going from here to the reduced species. Okay, that's what we mean by reduction species. That's what indicates the x-axis. That's what is indicated in the x-axis. So along this direction, there is cathodic reduction. So this is the cathodic reduction direction. And in this direction, there is anodic oxidation. You go from a reduced species to the oxidized species. Then we are indicating two electrode potential. One is more positive than the other. V2 is more positive than the other. V2 is more anodic than the other. The potential couples to the energy of electrons, and it varies the electrochemical potential of the electrons. When you go to a more anodic potential, let's say V2, these electrons are stabilized to a greater extent. The chemical potential is reduced, that is, it becomes more stable. And that change in energy level, change in chemical potential of electron is indicated by this change. Okay, so this is, let's say, indicates the energy level of R. That's not sensitive. In this picture, it's not sensitive to the electrode potential. The electrode potential couples to the chemical potential of the electrons. And because the electrons are present only in this state, when you change the electrode potential, that varies the energy level in the following manner. When, let's say, delta V is the difference between V2 and V1. And when the electrode potential is changed in that manner, the energy level of electrons is also changed by F delta V. It is, this electrochemical reaction is an activated process. Again, this is analogous to what you've seen in a chemical reaction, right? So in a chemical reaction, you might have defined what's called a transition state or an activated state to go from, let's say, reactants to products. You along this direction or along this direction, doesn't matter. You have to go through a higher energy state, which is called an activated state. The transition state has a more formal definition. It's a saddle point in the potential energy surface. Even if you don't understand that term, that's all right. There's a formal definition for a transition state. That's not important, but at least you should know that there is an activated state which is higher than either this state or these states, and you have to go through that state, this higher energy state, to transform from this state to this state or from this state to this state. Okay, so this electron transfer reaction is an activated process. This activated state controls the activation barrier and in effect controls the rate of these electron transfer reaction. All these things are analogous to what you have seen in chemical kinetics or in a class on chemical reaction engineering or a class on catalysis. Okay, so go back to these notions, try to build your intuition in chemical kinetics and extend that intuition to electrochemical kinetics. Okay, that's the way I work. The rate of the cathodic reaction is cathodic reduction. It involves two things: combination of electrons from the electrode, transfer of electrons from the electrode to the oxidized species. So that is the forward rate. Okay, rate is indicated here. F indicates forward, cathodic reaction, that is the reduction reaction. It indicates the concentration of C naught. Okay, so this C is C naught is the concentration. Okay, concentration of this oxidized species. So the rate involves, in a way, collision of the electron from the metal electrode to the oxidized species in solution. I am using this term collision to make an analogy with what you've seen in your chemical kinetics. Okay, there is this collision theories that are utilized. So likewise, we are having similar notions in electrochemical system. So the rate of forward reaction will involve a collision of electrons and oxidized species. In a way, the activity of electrons is convoluted into this term. Okay, so we had elaborated on this term in the previous lecture, again on Butler-Volmer equation. Go back to that lecture and interpret this quantity. Okay, you will see that the activity of electrons is convoluted into this term. So the rate of forward reaction is a product of concentration times this proportionality factor, and it is also modulated by the activation barrier for the forward reaction. Okay, so there are different activation barriers. There are two different activation barriers depending upon whether you want to go from this state to this state or from this state to this state. Okay, so one is this activation barrier and another is this activation barrier. So here we are indicating the rate of cathodic reaction. We can also indicate the rate of anodic reaction. The essence of electrochemical reactions is that you are manipulating the electrode potential. This electrode potential is going to control dominantly the chemical potential of the electrons, which in effect controls the energy of the activated state. All right. In response to change in the energy of the activated state, the activation energy also changes. Because of the change in activation energy, the rate also changes. We have indicated few other quantities here, which we didn't elaborate in the previous slide. That is this beta and 1 minus beta. Okay, so it looks like a complicated definition. We will see why it is defined in this manner. We cannot do total justice to this definition, because if you want to understand why these are defined in the following manner, we have to go to more molecular principles involving quantum statistical mechanics. Marcus won a Nobel Prize for clarifying these issues. And there are three different classes of theories called the Marcus theory, Marcus-Husch theory, Marcus-Husch-Chitsey theory. So all these things are just names for you. All I'm trying to point out is there are deeper theories which will enable you to get a more quantitative estimate of beta, which also alpha in the previous lecture, from principles of quantum statistical mechanics. Okay, right here, we are not going to do those, discuss those theories. We are going to just say that these are something that can be measured from experiments. We're going to interpret, okay, based on this potential energy surface. How are we going to interpret? 1 minus beta is the fraction of total energy change. What is the total energy change? There is a total energy change because of variation electrode potential. When you vary the electrode potential by delta V, the total energy change is F delta V. Okay. 1 minus beta is the fraction of the total energy change that modulates the activation energy of the cathodic reaction. Okay, this is the change in the activation energy. You can also define beta as the fraction modulating the anodic oxidation. Again, this will become clear just in a minute. This beta is typically has a value of around 0.5. It doesn't matter what is the exact value. It's a positive quantity, has a value ranging from, let's say, 0.35 to 0.5. Let's look at the change in activation energies in the cathodic reaction and the anodic reaction. The activation barrier at a potential V2 can be obtained from the activation barrier at potential V1 plus the change in energy because of change in potential. Okay, so this is the direction we are in considering, right? If this goes down, that is your energy of the reactant state goes down, your activation barrier is going to increase by the amount F delta V, but the activated state energy decreases. Okay, so corresponding to increase in the reactant state, there is a decrease in the energy of the activated state by this amount. Okay, this is amount indicated here. If you add all the three quantities, you get this quantity. Okay, delta G. This double dagger indicates the double dagger was introduced by Henry Eyring. Okay, he was the pioneer in transition state theory, I think in 1935, I think, if I remember right. He developed all these theories. He's one of the greatest physical chemists who didn't get a Nobel Prize, like G.N. Lewis, Slater. Henry Eyring is one another great physical chemist. He introduced a lot of important concepts in physical chemistry, but didn't get a Nobel Prize for transition state theory. One of the big reasons is that it could not, this transition state theory could not be easily extended to quantum mechanical system. A classical description was possible, but the extension to quantum mechanical systems was challenging. Okay, this is just this is, even if you didn't understand that statement, that's all right. I make such statements to perk up your interest to learn more. Okay, so even if all these statements are not very clear, that's all right, but at least you should know of these terms and the dominant scientists who developed these theories, okay, so that you can go and read up more. All right, coming back, the cathodic activation barrier is modulated in this manner. There is an activation barrier at V1, plus there's another term because of changes in activation barrier. You can write a similar expression for anodic reaction. Here, there is only one change, only the change in the energy of the activated state, because this state doesn't couple to change in electrode potential. We can change the activation barrier relevant to anodic reaction by just incorporating this change. Okay, that's what we have done here. Both these things then can be included into your rate expression. So you can discuss the rate at potential V2 in terms of concentration of the oxidized species times a proportionality constant times the relevant activation barrier, which this quantity we derived in the previous slide. So this is the activation barrier relevant to V2. What is important are changes in potential. Okay? Changes in potential bring forth changes in activation barrier. It is not absolute potential that are important. In fact, absolute potentials cannot even be measured. Okay? You can only measure potential with respect to something. In fact, only differences matter. So because only differences matter, we can take this V1 to be zero potential. Okay, we can reference it to some zero potential, and we can talk about delta V with respect to that zero. Okay, so that brings about certain simplifications in notation. We're going to call this V1 as being zero potential, and because of that, we can talk about the rate constant at zero potential and indicate that in this manner. So we are going to pull up this term and this term. This term becomes this term because V1 is 0. So that will become a constant. Okay, that is a constant. With respect to that constant, we are going to discuss changes in activation energy, which is this term. All right. So we're going to pull up this term and represent this as Kc, and we are going to write the modulation of rates at a given potential V with respect to a zero potential, and write it as Kc, which again Kc is this expression, Kc times the concentration of the oxidized species times all this quantity. If V1 is 0, V2 is V, that is this expression. Again, I want you to contrast all these things with all these things, because these kinds of expression that you see in an electrochemical system with Arrhenius expression. Okay, in your Arrhenius expression, there is this E act, energy of the activated state, and this term is also present, and then there is a frequency factor A. Okay, go back to your Arrhenius expression, extend your intuition from Arrhenius expression to the electrochemical system. That's a way to understand these things. Okay, so that is the rate of cathodic reaction. By convention, cathodic currents are indicated by a negative quantity. So just to be consistent with that, we are introducing a negative sign. Cathodic reaction is always as a negative sign, and the anodic reaction as a positive sign. So cathodic reaction is indicated in this manner. And in a similar manner, we can indicate the anodic reaction. Okay, anodic reaction will involve the activation barrier in the opposite direction. We can write the rate of anodic reaction, which can be connected to anodic current, which is a positive quantity. We can write in the following manner. Okay. Okay. We are going to introduce another quantity. Because we are going to utilize certain principles of chemical equilibrium to obtain the ratio of two quantities. that is Ka and Kc, are related at equilibrium. The ratio is related at equilibrium. At equilibrium, the net rate is zero. So the rate of cathodic processes at a single electrode electrolyte interface. Okay, here we are not talking about two different electrodes. So typically in electrochemical cell, you have an anode and cathode. But in this discussion, we are talking about anodic process and cathodic process occurring at a single electrode. Okay, that single electrode, when it is at equilibrium potential, which we refer to as the null potential in the previous lecture, the rate of anodic processes is the same as the rate of cathodic process. So this U is the null potential. Using the rates expressions that were derived in the previous slide, we are going to write this expression. The rate of anodic processes is same as the rate of cathodic processes. We can write this mathematical expression. That is also going to help me simplify the previous expression. Okay, we'll see. Okay, this rate at equilibrium is called exchange current density. As I've mentioned in the previous lectures, the equilibrium is a dynamic equilibrium. Okay, even though there is no net rate, there is always cathodic processes occurring, anodic processes. Only that the overall anodic process is same as the rate of the cathodic process. Okay, so even though the net rates are the same, net rate is zero, there is always transfer of modification of this ion to this system and this system to this ion. Okay, that is always occurring. All right, we are going to call this the exchange current density. What is the significance of exchange current density? In a way, exchange current density is indicative of the electrocatalytic processes occurring at that single electrode electrolyte interface. If the exchange current density is large, that means the relevant activation barrier, okay, this activation barrier is less. And if the activation barrier is less, that means that electrode is a better electrocatalyst for transforming this species into these species, and it is also able to transform this species into this species. The activation barrier for both these processes is less. Okay, that's the significance of exchange current density. All right. Okay. Using this expression for exchange current density, I'm going to write the anodic currents at a given potential V. Okay, so this anodic potential is a function of potential V. So we are now not at equilibrium. Okay, at a potential V, which is different from the null potential U, there is finite currents that are flowing. Okay, so depending whether V is above U, whether you are above U or below U, there can be net anodic or cathodic currents, but you are no longer at equilibrium and there are finite currents. However, we are going to utilize the rate constant expressions that we are derived using principles of chemical equilibrium and use such rate constant expressions in a system that is not in chemical equilibrium. Okay, whenever you are not in null potential, you are not in chemical equilibrium, but still we are going to use expressions that we derived using chemical equilibrium, electrochemical equilibrium principles, and obtain rate expressions at non-equilibrium conditions. Here we have divided and multiplied by the same expression. Why did we do that? We are going to use this expression for exchange current density to simplify the expression for anodic current. Okay, so combining these two mathematical expression, we can write the anodic current density and the cathodic current density. Okay, so using the exchange current density formula, we have simplified the anodic current density into this expression. Anodic current density at a potential V depends upon a constant factor. Okay, I naught, this is an exchange current density, multiplied by this expression. Here, what are we changing? We are changing V, and in response to V, we are getting anodic currents. Okay, we can write a similar expression for cathodic currents. Cathodic current at a potential V is given by a constant factor, which is the exchange current density, and that is modulated by an exponential term given by this expression. Okay, this quantity V minus U, okay, is called the O potential. As you can see here, the way we have defined, the O potential can be a positive quantity or negative quantity, but the modulus of the O potential is indicative of how far you are from the null potential. Okay, the modulus in a way is going to tell you how much is the cathodic or anodic processes is going to vary from the expressions from their rates at null potential. At null potential, the rates were exchange current density. As you move away from the null potential to a potential V, the rate expressions for anodic and cathodic processes vary in an exponential manner, may increase or decrease at an exponential manner. This is called the O potential. What does S indicate? Okay, S does not indicate solute or solvent. This indicates what is occurring at the surface of the electrode. Okay, all these electron transfer reactions are occurring at the electrode surface. So this is the O potential present at the electrode surface, which modulates the activation barrier, and hence it modulates the relevant rates, anodic and cathodic rates. Remember, when we discuss the electrode potential or an electrochemical potential, this electrochemical potential is a composite potential. Okay, it is a potential that is indicative of the potential present at the electrode, also indicative of the potential present in the electrolyte side of the double layer. Okay, so we had discussed, even though these things are not legible, please go back and look at this figure. When we introduce electrochemical kinetics, we elaborated on the meaning of this figure, but all I want to indicate here is when we talk about an electrochemical potential, it is indicative of two quantities. There is a potential present at the electrode surface, and there is another potential that is present at the electrolyte medium. Okay, so in practice, we will often be decomposing this potential V into two quantities. That is a potential of the metal and there is the potential of the solution that can be measured using a reference electrode placed in this region. Okay, so this we will talk about this measurement later. Okay, how you have to make that measurement. But right now, all I'm going to state is that this potential phi solution can be made using a reference electrode placed in this region. Okay, and this potential U is also measured using a similar or the same reference electrode. Okay, so against the same reference electrode. Okay, so physically you can have two different reference electrodes. Okay, so this equilibrium potential is referenced against a reference electrode, and such a reference electrode is placed in this region to measure phi s, that is of relevance. Okay, again phi m can be measured with the voltmeter. All right. I'm sure there'll be questions on this. We can discuss this in the discussion session. Okay. So we are going to decompose V in this manner. That will be done when you utilize these equations in practice. Putting all these things together, that is the net current in a single electrode electrolyte interface. We are not talking about two electrodes. We are talking about a single electrode electrolyte interface. Single electrode, the net current depends upon anodic processes and the cathodic process. When summed together, will give you the net current. I have just put together these expressions and given this overall expression for I. It is the product of two quantities. This is the exchange current density, which is a constant, and this quantity, which depends upon the surface overpotential. Okay, this is called the Butler-Volmer equation, which is the central electrochemical kinetic equation. Okay, so we derived the Butler-Volmer equation in a different manner in the previous lecture. Here we have used certain arguments related to potential energy surface and presented the Butler-Volmer equation. Okay, so overall, this presentation of potential energy surface adds to the insight. Okay, so what is the insight? Okay, when you change the electrode potential, how does the electrode potential couple to the electronic energy levels? And when it couples in that manner, you are reducing or modulating the chemical potential of electrons. And when you modulate the chemical potential of electrons by modulating the potential, electrode potential, you're also changing the activation barriers, okay? Because the energy of the activated state is also changed. Because of such changes, the activation barrier also changes, because of which the rates of electrochemical reactions also changes. Okay, so all these concepts are incorporated into the Butler-Volmer equation. I will conclude this lecture here, and I'm sure there will be questions which we can take up in the discussion session. Thank you.